In section 14.3a, we were working with projectiles. So we were firing things out of cannons and, throwing balls, that kind of thing. But we want to take those concepts and apply them to generalized motion, not just for projectiles, but we want to be able to work with motion for all vector valued functions. Now, remember that r of t is your position, right? So you assume that r of t is your position function. And if that's the case, then velocity is v of t is the derivative of position. Speed, which we dealt with a little bit in the previous section, is the magnitude of your velocity. So that would be the magnitude of your derivative of position. And then acceleration, which is a of t, is the derivative of velocity, which means it's the second derivative of position. And just for fun, let me just throw in some units over here. So for r of t, the most common one for us is meters, and this would be meters per second. This would be meters per second. So velocity would be meters per second, speed would be meters per second, and acceleration would be meters per second squared, right? So this would be metric units that I'm doing here. And for fun, we could also throw in imperial units. So position would be in feet most often, and then feet per second, if we're talking about projectiles and stuff like that, feet per second. And of course, there's also miles and hours. So miles per hour is another one. And this would be feet per second squared. These are just examples of the units that are possible. Okay, so we kind of want to look at parameterizations a bit. So we're going to drive that with looking at motion in a line. So we're going to consider the parameterizations of a line through the origin. So notice that it goes through the origin. So that would be 0, 0, 0 in vector form with a direction vector of 2, 3, 6. So we're going to parameterize this line using the standard form for the equation of a line in R cubed. Now the standard form is the line would be equal to the direction vector times t plus the point, right, in vector form. Okay, so if my direction vector, this is v right here, direction vector. That's my direction vector. And so it would be 2, 3, 6 times t plus the origin, which is 0, 0, 0. So that means that I could parameterize this line with 2t, 3t, and 6t. Now, there's a relationship going on between these variables that you could define any particular way you wanted. I'm actually going to solve in terms of x for these other variables. So just take a moment and think about this. If x is equal to 2t, then t would be equal to 1/2 x, if you will. And so that means that instead of 2t, I would have x. Then 3t would be 3 times 1/2 x. And then the z component would be 6 times 1/2 x, which would make it x 3/2 x 3x. Think about what this is showing. The relationship here is that whatever x is, z is 3 times that much. Right? As x. And this is 3/2 of x. Right? Which I know that's what it's saying, but think about what that means in terms of pace. So we could use that relationship to parameterize any particular way we want it. And for the record, there's nothing special about x. I could have done this with z just as easily. Set 6t equal to z and solved. It's just, x was the smallest one, so it's the easiest one to work with. Okay, so if I do this for L2, L2 of x, if I let x be 4t instead of 2t, which is what it originally was. So if I let x be 4t, so let's use this relationship that we're seeing here. 4t, 3 halves times 4t, and then 3 times 4t. And for the record, you don't have to do this. I mean, how do I get 4t out of the original? I just multiply it by 2, right? So 2 times 2 would get me 4 and so on. So I would have 4t for my start. 2 goes into 4 twice. 2 times 3 is 6, which 3 times 2 makes 6. And then 6 times 2, i.e. 3 times 4, is 12. All right, so there's L2. All right, what about L3? Well, this is going to be a little different. It's basically taking the original and multiplying it by t, right? So if I took the original and multiplied everything by t, I would have it. Or I could put it into that modified form I have. 2t squared, 3 halves times 2t squared, and then 3 times 2t squared, which would be 2t squared for the x, 3t squared for the y, and then 6t squared for the z. And you can see that would be the same thing as multiplying each of these terms by t. Right? That would get you there. But it still works. All right, let's try one more. Let's do L4. I'll do it in green here. L4 of t is, well, it's just using square roots instead. So it'd be 2 square root of t, 3 halves times 2 square root of t, 3 times 2 square root of t. Okay, so that's 2 square root of t. 2 goes into 2 once, so 3 square root of t, and then 6 square root of t. There we go. Okay, so now what's happening here? What's going on with all these pictures, right? So what do the graphs of all of this look like? And to do that, or to look at that, I did it in Maple. So let's look at my Maple graph. All right, so I put the 4 parameterizations in here. I didn't like the lowercase l because it looked like an I, so I did an uppercase L. And then I graphed them all as space curves, and I tried to match the colors to the colors on the paper, but it's not perfect. So the blue one, if you can see it, it's in there. It's right in there. It kind of stops off at a z of about 30. So that's the blue one right there. And then the green one's that little short one. Right, that was the 4th one. So that's L4. L1 is actually right there, the blue. And then the purple kind of comes up to a z of about 60. See right there? And then the pink one is the biggest one. Actually, maybe I'll increase my transparency on the pink one so you can kind of see through it. Oops, I went the wrong way. I meant to increase my transparency, and I decreased it accidentally. There you go. Now you can see them. So there's the green. There's the blue. It kind of looks purple because it's maxed with pink. And then there's the purple one right there. Actually, I just increased the transparency even more on the pink one, so it's almost translucent. But you can really see the green, the blue, and the purple then. They're right there to match my colors. All right, so what are we noticing? Well, they're all on the same trajectory, right? They're all there. It's just they go to different distances depending on which one you're looking at. So let's write that. Okay, so they are all the same line, right? They're all pointing in the same direction, but they're different lengths for a fixed domain of f. So if you look at the way I did this, I did all of them with a domain of 0 to 5. So at t equals 5, they got as far as you can see. So the green one got the least far, and then the blue one got a little bit further, the purple one got further than that, and the pink one got the farthest of all. So you can see that they're getting farther along for a fixed domain.